recording. So what we're going to talk about today is another calculus tool for helping us figure out how a given function is changing. So far, we've talked about finding a first derivative, like taking the derivative of a function. And what that will tell you is whether the function is increasing. In other words, if you get a positive slope at a given x value, you know your function's going up. If you get a negative slope, you know the function's going down, right? And we talked about these in the context of marginal values. In other words, like a marginal profit. If I get +1, that means if I make and sell one more of my product, I'll get another dollar in profit. If I get -1, though, it means profit's going down if I make and sell one more thing. So far we've used the derivative to tell us whether something's increasing or decreasing. And what we're going to learn today is how to use the second derivative to tell how fast that's happening. Also, we want to talk about places in our function where our derivative value is 0. That means the function is turning around there. It's going from either increasing to decreasing or the other way around. Okay, these are the hills and valleys in a polynomial function. If you think about it, you've got a horizontal tangent line at those turnaround points. So those might be good to find, particularly if you're going to use your function to make predictions about, when profits at a maximum or a minimum. Okay, those are those turnaround points. So I'm going to begin by sharing my browser with you, and we can take a look at where we are in the course. Okay, we're currently in week 6. You can see that right here. And again, the recording from Monday, from a version of Monday's class, is already in here. And I'll put today's recording in this section. Okay, so hopefully everybody is able to find the recordings. They're usually the very first thing in each of the week by week. Okay, so we did rates in real life in class on Monday, and today we're going to do second derivative and concavity. So I'm going to be using these second derivative and concavity notes. Okay, as far as assignments this week, of course, you've got the 2 homework sections, which again, you can ask me questions on any of those homework questions by clicking that message instructor link at the bottom. Okay, that will send me an email and I'll be able to respond to you about the specific problem you're working on. We also have our second grade check, which is due this week. Okay, this again is an opportunity for us to talk about how you think you're doing in the course and whether you need help or have any other concerns. Okay, so please, again, make sure you get to these by Sunday the 3rd. But right now I'm going to be opening these notes. So give me a moment to do that and I'll share them with you. Okay, and let's just share that content. Okay, now everybody should be seeing Math 213, second derivative and concavity. I'm going to open the chat in case anybody has questions as we're going along. Again, these guided notes are excerpted from the readings. They don't cover everything in the readings, so it's still a good idea to go back and read the online textbook that I've put links to in the modules. But pretty much these are the highlights. Okay, so again, you can follow along online. You have the notes right there. Okay, and these yellow boxes are kind of the excerpted important points. So we mentioned taking the first derivative. What you've been doing when we said take the derivative using those derivative rules is you're taking the first derivative. You're doing it once. Okay, if we do it a second time, in other words, we take the first derivative and differentiate it again, that's called the second derivative. Okay, It's a rate of change of a rate of change. You might remember when we were in class on Monday, we talked about acceleration, which was a rate of a rate. That's what the second derivative is telling you. Okay, it's how fast your rate of change is changing. Either it's speeding up or it's slowing down. Okay, now notation for second derivative is essentially a double prime. Okay, so essentially it's the derivative of f prime, and we're going to write it as f double prime of x or y double prime. Okay, and that just means second derivative. And in case you're thinking, wait, what, can I keep doing this? Yes. Okay, once you get beyond the second derivative, like if you want a third derivative, and again, I can't think of a reason outside of physics you would need such a thing, but you do it like this. Okay, so it basically has the derivative you're taking in parentheses as a superscript, so you don't confuse it with a power. Okay, so that's the notation for higher derivatives. Pretty much in this course, we're only going to be looking at first and second derivatives because they have meaning in the applied contexts we care about. My preference for notation is to use f double prime, and I'll use that almost always. The differential or the Leibniz notation is extremely confusing. Okay, you just read them as the second derivative of f, but if you notice, it's the d that's squared, not the function, and then the dx at the bottom is squared. Okay, Leibniz notation is only useful when there are several variables you could be differentiating with respect to. So far, we've only talked about functions of x. Okay, but when we talk about implicit differentiation, I'm going to switch to this differential notation because it'll make things clearer, believe it or not. Okay, so for now, just use the f double prime. All right, now what does f double prime tell you, the second derivative? Okay, so if f double prime, if your second derivative is positive on an interval, that means the function is concave up. Okay, you can think of it looking like this diagram down here. This is what a concave up function looks like. Okay, one way people think of it as is concave up. If you were to take a watering can and pour water on this graph, concave up holds water. Okay, you can see it's kind of like a little cup here. Here's another concave up piece. So if I poured water here on this graph, okay, I'd have water stuck in the bottoms of the concave up pieces, all right? And what that tells you is the function f is either increasing or decreasing at an increasing rate. In other words, it's speeding up or it's slowing down fast, okay? So over here, the function is slowing down fast, and here it's speeding up fast, all right? When f double prime, your second derivative, is negative on an interval, it means the function's concave down, and that means it's increasing at a slower rate or decreasing at a slower rate. Okay, and you can imagine the same thing if I were to pour water on this graph over here where it's concave down, it would spill the water. Okay, so does everybody think they understand what concave up and down mean graphically? Okay, questions? And it's called concavity. Okay, now I realize we haven't done anything with derivatives, but questions on concavity as it applies to this graph. Okay. No? Take a minute and look. All right. So again, anywhere where the graph's concave up, I'm going to have a positive second derivative. Okay, another quick way to remember that is concave up. Okay, your second derivative is positive, smiley face, right? Concave down, your second derivative is negative, frowny face. Again, these are two positive signs to apply to second derivative, right? Two negative signs apply to second derivative. Okay, and here's concave up, concave down. So that little mnemonic kind of helps you remember how to use the second derivative, what it tells you about concavity. Okay. Now you might be sitting here looking at the dotted lines saying, okay, what's with the dotted lines? Well, think about it. My graph's concave up here, concave down here. That must mean it needs to switch at some point, okay? And the dotted lines are showing you these switching points, okay? They're called inflection points. It's a point on the graph where the concavity of the function changes from concave up to down or from down to up, okay? It's also a point on the graph where the second derivative changes sign. Okay, usually the second derivative is 0 at an inflection point. Okay, there's some weirdnesses with undefined and stuff like that. That's why I'm hedging my bets with the word usually. Okay, but think about it. If your second derivative's positive here and negative here, it needs to go through 0 somewhere. Likewise, if it's negative here and positive here, it had to go through 0 somewhere to make that change. All right, so usually at an inflection point, your second derivative will be 0. Okay. Questions on that? Again, I'm going slow so you can ask. Okay. All right, let's take a look at this graph here. Okay. And what we kind of want to do is take a look at what we think is going on at each place. Okay. First of all, let me ask you, where is the first derivative equal to 0? Okay, so I'm asking you about f prime. Okay, remember f prime is tracking the slope of a tangent line. Where is it 0? Anybody have any suggestions? You can type in the chat, you can unmute, but I'm asking a question. Okay, you can give me letters as the answers, right? A, B, C, D, E, F, G, H. So where is f prime, the first derivative, 0? Okay, just as a memory jog, horizontal tangent. Okay, Gil's got A as a suggestion. Anywhere else? Okay, Rich, A, C, E, maybe. Okay, H. Okay, let's go along with A, C. E is kind of weird. Okay, because think about your tangent line coming down this graph, right? When it gets right here, it does this. Okay, so it's not horizontal. It's vertical there. Okay. So I'm not gonna include E. Okay, but so far we're picking these points. A, C, H. Is there any other turnaround point? F. Okay, good. Okay, these are all points where the graph turns around, and I realize the graph is doing something at E. Okay, E is called a cusp. Okay, E is called a cusp. It's not technically a turnaround point. Okay, sort of, kind of. Okay, because it's got a vertical tangent line at E, the derivative's undefined there. Okay, so you kind of want to check. Okay. Okay, that doesn't mean you can't tell things about that point on the graph. It just means you've got to be careful. Okay, so here are the places where our derivative, first derivative, 0. Okay, then let's ask another question about f double prime. Where is f double prime of x positive? In other words, where is the graph concave up? Where's the graph concave up? Okay, we're looking at the same picture. It's okay if you use the same values. Remember, concave up holds water. Okay, A and H, good for you, Andres. Okay, so then where is F double prime negative? That's concave down. All right, that's the spills water. Okay, good for you, Jennifer. That's C and F. Okay. All right, so you've got it. Okay, then what about these points B, D, and G? Okay, so let me ask you about those points. Okay, B, D, and G, you told me my second derivative is positive here and negative here. Well, the graph goes through point B on the way from C to E. Okay, and it has to find a way to go from positive to negative, right? Second derivative. So B is one of those points where the second derivative is 0. Same thing here, maybe, okay, with D, okay, because it goes from concave down, okay, and it doesn't quite become concave up. All right, so D is one of those iffy things, okay. G for sure, it's going from concave down to concave up. So G looks like one of those points where the second derivative may be 0. Okay, may be inflection points. Okay, everybody kind of understand what these inflection points are? It's where the concavity is switching. Okay, if you actually look at this on a high resolution graph, more like Desmos, you can almost kind of see the concavity change. This is kind of not high res, so it's real hard to see anything. I'm using what I know about calculus, namely, we're going from concave up to concave down, from a positive to a negative second derivative. It has to go through 0 somewhere. Okay, and B looks like a reasonable point. Okay, so anybody got questions? on this idea of inflection points. Okay, the idea. Okay, we haven't done anything with them. Okay, but just want to make sure you understand they're there. Okay, it's not something that we've paid a lot of attention to. Anybody questions? Okay. All good. Okay. Anybody else questions? Again, I'm not seeing all of you, so I can't see the furrowed brow or the face. Like, I don't know. Okay, so please ask if it's not clear. All righty. So let's take a look at some word problems. Okay, these are the types of situations you're going to run into in real life. Okay, and so what we're going to try to do is we're going to try to represent the statement with derivatives. Okay, derivatives in the sense of calculus derivatives, right? So it says in these problems, each quotation is a statement about a quantity of something changing over time. Let f of t represent the quantity at time t. So f of t is your output, right? In all of these, your input's time that's just ticking along. For each quotation, tell what f of t represents and whether the first or second derivatives are positive or negative. Now, we've got to remember, okay, first derivative's positive when the function's increasing, negative when it's decreasing. It's the slope of a tangent line. Second derivative, positive when the function's concave up, accelerating, okay, negative when the function's concave down, decelerating. Okay, so you have to kind of remember that, right? Maybe have a cheat sheet over here, like f prime, positive if f is increasing, negative if f is decreasing. Okay, it's perfectly okay to make yourself a cheat sheet, right? F double prime of x, positive if I guess, how should we say this? How did they say it? Okay, so function is increasing or decreasing at an increasing rate. An increasing rate. Okay, and again, I realize when people talk about this, they use everyday English, like speeding up, slowing down. Be careful, okay? Accelerating, decelerating is better, okay? But a lot of people seem to only think of, you know, those in terms of speed, and that can be dangerous too, okay? So let's take a look at these and see if first we can figure out what the function output is. Okay, so what in this one, what's f of t? Okay, take a look at the three sentences. Okay, what's f of t in the first one? Okay, in 1a, what's f of t? Okay, in 1a, what's f of t? Anybody?
F
Okay.
of t is time, right?
Nope, t is time. So what's f of t? What quantity is it? I'm asking you for a word. Okay, what quantity? So your question is well taken. What quantity depends on time? In
Could be
1A.
unemployment.
Unemployment, right? So in this one, I'm going to just underline f of t. Okay, unemployment is our output. Okay.
Oh, I see. Okay. I
Yeah,
wasn't even looking
understand what
down
they're
there.
asking? Yeah. A
Yeah.
lot of this is figuring out what in heaven's name are they asking for? Okay.
Yep,
So
I'm following now.
unemployment's our output. It depends on time. Okay. We're not looking for values. Okay. We're not looking for values. We just wanted to identify what's input, what's output. So in 1A, output's unemployment, input's time. Okay. Now let's look at rates. Okay, let's look at rates. Okay, unemployment rose again. So let me ask you, is unemployment increasing or decreasing?
Decreasing?
It's increasing if it rose, right? Okay, so rose, increasing. And what does that tell you about the first derivative? Okay, basically, I'm just asking for
It's going to be
signs.
positive.
It's positive, yes. So that means f prime of t is positive. Okay, but take a look at what comes after but. Yes, you got it, Richard. The rate of increase is smaller. The rate of the rate is smaller. That means it's going down. Okay, and we said over here, if it's increasing or decreasing at a decreasing rate, that means f double prime is negative. Okay, is everybody seeing that? Not of X or T, sorry. Okay, does everybody understand what this means? Okay, if you're going to use calculus, like to do any kind of modeling, this kind of wordage has to make sense to you. Okay. Questions on 1A. Okay, try 1B. Okay, first thing, what's the output? What's f of t? And again, you can unmute and talk to me. Okay, good, Richard. Profits. Okay, that's your output. Now they said they declined. So are we increasing or decreasing?
Decreasing.
Okay, and what does that tell you about f prime of t?
It is negative.
Yay. Okay, but at a slower rate. So they're telling you about the rate of the decrease. The decrease is slowing down, right? So it's not plummeting anymore. The decrease is slowing down. So what does that tell you about f double prime?
So negative.
Yeah, negative, right? Slower rate means less than, right? A
Okay.
decreasing rate. So here, both first and second derivatives are negative. All right, let's try 1C. Okay, first of all, what's your output? What's f of t?
Population.
Yep, population. Underline it. Okay, and they're saying it's still rising. So what's that? Increase or decrease?
Increase. Positive.
Yep. And at a faster rate. So what about the second derivative?
That means the second derivative is positive.
Yep. Okay. Faster means increasing. Slower means decreasing. Okay. At least in colloquial English. Okay. Hardly anybody talks like what they did in 1A. The rate of increase is smaller than last month. I can imagine this coming from a statistician or an accountant. Okay. But ordinary folks, not those of us like you and me who have a math background, typically say it like this. Okay, so you have to be able to make the connection between slower rate, meaning decreasing rate, and faster rate, meaning increasing rate. Okay, let's try 2. All right, 2A. What's my output in 2A?
Temperature.
The child's temperature, right? Okay. Now, without any scaffolding, what do you think the first derivative sign is?
Positive.
Positive, because it's rising. Okay. And how about the second derivative? Anybody ideas on F double prime?
Well, is it gonna be?
What it
Oh yeah, it's
means.
gonna be positive
Positive.
Why positive?
because it's still going up, but it's still slower than it was.
Okay, remember, the first
negative?
derivative tells you whether it's increasing or decreasing. The second derivative tells you whether that rate is speeding up or slowing down. So don't muddle the two, okay? The first derivative says it's going up. We handle that. The second derivative tells you, is that rate speeding up or slowing down? So what do you think? Is the rise speeding up or is the rise slowing down? Like it's still going up, but it's not going up as fast as it used to.
It's slowing down.
It's slowing down. So this would be negative.
Negative.
Okay. Understand that the second derivative is controlling your acceleration. Okay. Not your speed. Okay. Yeah. It's real easy to get them confused, like mix them together. Okay. But again, keep this cheat sheet up here in mind. Okay. These two things tell you different information. All right. Let's try 2B. Okay. What's my output? First of all, what's F of T?
Number of whales.
The number of whales that I'm tracking. Okay. First derivative sign.
Negative.
Yeah, it's negative because they're decreasing. Okay, now talk about the rate of decrease. Is that rate speeding up or slowing down?
Slowing down.
Yep. Okay, so both first and second derivatives, okay, are negative. Okay. And last one, number of people with the flu is rising and at a faster rate than last month. Okay, first of all, what's F of T? What's my output?
The number of people.
Well, people with the flu. Okay. First derivative. What about F prime of T?
Positive.
Positive because we are saying they're rising. Okay. Now we're asking about the rate of the rise. Is that rate speeding up or is it slowing down?
Speeding up.
Speeding up. Okay. So this was kind of, I really liked this exercise. You probably didn't like it so much, but it helps you solve word problems. Okay. Or at least interpret what comes out of doing calculus. Okay. Remember, if you're going to use this for any kind of modeling and you're going to be talking to coworkers or clients or whatever, management, you're going to have to explain it like this. Okay. You're not going to tell them F double prime is positive. You're going to tell them our rate is increasing at a faster rate than it was last month. Okay, so that's the point. Anybody questions about the exercise? Questions so far?
I had a question.
Sure, go ahead, Jennifer.
If we already found the output, what would be the input like in this exercise?
In all of these, okay, in all of these, your input is time, okay, because they tell you up here, f of t represents a quantity at time t, but the words would tell you as well, because over here, we're talking about increases compared to last month, last year, a few hours ago, last year, last month. Those are all time words, okay? So that's our input variable is time. And all of the output variables that we underlined, those depend on time, like their value is going to change with time. Does that make sense?
Yes, thank you.
Okay. Anybody else have a question before we move on? Okay. Now here's an opportunity to play with interval notation. Okay, so let's take a look at this graph. Okay. Remember, you're going to give us X intervals. Okay. So essentially, we're going to talk about where the graph is concave up and where it's concave down. Okay. Again, it's not clear where the inflection points are. Okay, we can kind of label them here. Okay, I'll label some inflection points. Okay, that's where the graph changes concavity. Okay, I'll just help you out with that. Okay, and now you can pretty much see, and again, even this one is not terribly clear, so I can kind of eliminate that one, and I'll move it over here. Okay, so let's call those your inflection points. Okay, so if those are the inflection points, where's the graph concave up? Where does it hold water?
5,
5,
Okay, but give me an interval.
3, 7,
Okay, so you would say 3, 7. They're both X values. And we're not saying what's happening at 3 and 7 because concavity is changing there, right? So I'm not including those. Please remember, this is not an ordered pair. It's an interval, and both of these are X values. Okay, the fact that I have parentheses around it means that I'm not including 3 and I'm not including 7 because the concavity is changing there. Okay, and again, since I have a really low res graph, I'm kind of telling you, let's let concavity change at 0. Okay, how about concave down? Where does the graph spill water?
is it 0 and 3?
0 to 3, good for you. Again, these are both X values. Okay, so I have a graph that's concave down from 0 to 3 and then concave up from 3 out to 7. Okay, and I'm kind of guessing these are inflection points. Without seeing more of the graph, I'm not really sure what's happening out here. Okay, this may keep going up or it may turn around and go down again. Okay, so I'm kind of making things simple for you by saying the graph kind of ends here. So let's just make that like an inflection point. Okay. Try this one. Okay, try this one. Here, I'm not going to give you the inflection points. Okay, take a minute and look at this one and see if you can come up with the concave up and concave down intervals. Okay, you can put them in the chat or you can unmute and speak them. Again, imagine it raining on your graph. Where are the parts that would hold water? Okay, Richard has some concave up suggestions, 0 to 2 and 2 to 4. Okay, so he's identifying this as a possible inflection point, and he's pouring water in the graph, and he's noticing that those two intervals hold water. So they're both concave up, even though they're next to each other. Okay, and then he's got another one over here. Okay, maybe not 5, but maybe here. Okay. Everybody see it? Because again, 5, I'm pretty sure water would run right off at 5. Okay. Here's the inflection points. Okay. And they're kind of implying that 8's an inflection point, but it doesn't look like that to me. Okay. Because it looks like this graph's going to keep on going. Okay. They're just putting vertical lines here to help you see where those integer boundaries cross the graph. Okay. The graph isn't symmetrical. So that's okay. All right. So I would agree that the graph is concave up on the interval 0 to 2. Okay, and 2 to 4. Okay, and I'd also say maybe from 6 to 9. Okay, and you could kind of, put unions in here. Okay, some people might combine this first interval and say from 0 to 4, but it looks like some kind of weirdness is happening at 2. We kind of don't want to lose the weirdness. Okay, so you might have them as separate intervals, and I have the union sign in between to say or. Okay, that little U means or. Okay, concave down for sure, 4 to 6. Okay, that's where the water runs off. Okay, anybody questions? Okay. I'm going to just say here, inflection point. Okay, concavity changes, sign. Okay, and you might say second derivative is 0 or undefined. Now, just because the second derivative is undefined doesn't mean concavity has to change on either side. Okay. But in possible inflection points are where the second derivative is 0 or undefined. That's how you locate them. Right? Anybody questions on number 4? Questions on number 4? Please be able to identify intervals. Okay, you're going to need to do that on all the exams in this class. So if you need some extra support with interval notation, please ask me for it, okay? Right. All righty. Okay, here's an interesting exercise, okay? Let me just refresh your memory about college algebra, okay? Roots are what we refer to as real solutions, okay? They were also x-intercepts. Okay, so basically, if you think of, certain types of functions, okay, they may have complex solutions. You're not going to see that on a Cartesian plane. Okay, so let's take a look, and I will give you a hint. Let's try quadratic functions. Okay, everybody remembers what a quadratic function graph says, right? What does a quadratic function look like? What does a quadratic graph as? Anybody remember? If I graph y equals x squared, what do I get? No? Really? A U shape. Anybody remember what it's called?
Is it parabola?
A parabola. Yep. Okay. So here's my question. I'm going to draw a parabola somewhere on this graph for A, but I have to draw it so it has no x-intercepts. How can I do that?
So the bottom of the parabola is at y equals 1.
Okay, so here's the suggestion. Like that, right?
Yeah.
Not crossing the x-axis. Yay. Okay. Defined everywhere, and it is concave up, right? So they asked me to sketch the graph of a function which is defined and concave up everywhere. I gave you the massive hint of pick a quadratic because I know all polynomials are defined everywhere. There's no holes, there's no jumps, right? They're smooth. And a parabola, as long as I draw it with it has a positive leading coefficient, it's going to be concave up. It's going to open up. Okay, so that's concave up everywhere. Everybody see it? Anybody questions about it? Okay. Take our parabola and draw it so it has exactly one x-intercept. Where do I put it? So it touches the x-axis once. Where does it have to be? I mean, it can be anywhere on the x-axis, but it has to be there in a certain way. Can anybody describe it? Here's what you had. And now I want it to touch at one place on the x-axis. Where does it have to touch? On the parabola. Okay, yeah, it can touch at any x. But where on the parabola does it need to touch? Does anybody
Right at 0, 0.
right at 0, 0? But what point on the parabola needs to be there?
Like the very bottom.
The vertex, okay? It has to touch at the single point of its vertex. Okay? So must touch only on the vertex. Okay? You might remember in college algebra, this one, A, has no real solutions. This one has one real solution, but it's repeated. Okay, so this is something like a perfect square trinomial, okay, where you say get x minus 3 is the repeated root. This would be 0, okay? This is literally the graph of y equals x squared. Okay, so you're getting 0 twice as a root. How about exactly 2 roots? How do I make it cross twice?
We could bring the vertex down to -1.
Yeah, bring the vertex down, and then I get this. Okay, so basically, this has 2 real solutions. Okay, if you remember from college algebra, quadratics, okay, because their degree is 2, have to have 2 solutions all the time. But it matters whether they're all imaginary, whether they're one and repeated, or whether they're both real. That's what these 2 graphs are showing you, these 3 graphs, okay? Even a higher degree function like a cubic, since cubics do this, okay? Cubics, you know, are basically going to cross your x-axis somewhere, okay? So they have at least one real solution, okay? But they could have no other real solutions, or they could have repeated real solutions, just like quadratics. Now, I'm not using this graph because they told me it needs to be concave up everywhere, and this graph is not concave up everywhere. You can see it's concave down here. Okay, so cubics wouldn't do the trick. Quadratics make all of the conditions true. Okay. Anybody questions about this one? Okay, questions about 5? Questions on 5? Okay. All right. Now here's a kind of a mind bender. Here's part D. Okay. Now we don't need to use the quadratic. Okay, so think other than quadratic. Okay, just think if you could draw a graph that was concave up, it was defined everywhere. Concave up everywhere. And has 3 x-intercepts. Okay, that's what you're aiming for. This one's a trick question. This one's a trick question, but can anybody think of anything? I'm going to draw part of it for you. Okay, so here's 2 of the 3.
Would it be a polynomial?
Nope, not a polynomial. So don't think like cubic or 4th degree or 5th degree. Because again, it has to be concave up everywhere. If I go ahead and I draw 4th degree, it's going to do this, right? This is a concave down piece. And again, I'm warning you, it's tricky. It's a trick question.
What about like on those graphs that they had in the examples where it's like a point?
Fantastic. Good for you. Okay. So what he's thinking is a cusp. Okay.
Yes,
If
a
I have a cusp, I can do something like this. Right? Okay. So now what I've got is I've got 3 x-intercepts and the graph's concave up everywhere. The graph is defined at the cusp. Okay. But my first and second derivatives probably aren't defined there. Okay. But you can see it holds water everywhere. Okay, so kind of a trick question, not a polynomial, right? So good for you. Let's take a look at some of these. And again, we'll do some of them. Okay, we'll do some of them. And again, we're not going to get through all of the problems that I have here, but as long as we get through most of the different types, I think you'll be okay. So I reserve the right to kind of skip around. Like I'll do one and then you do one, and then we'll pick a different type of problem. Okay. But when I upload my notes, I'll have all of the problems done so you can see how to do all of them. Okay. So let's take a look at this one. It says it says a function and the values of x so that f prime of x equals 0 are given. Okay, so what they're saying here, these are the turnaround points. Okay, use the second derivative test to determine whether each point is a local maximum, a local minimum, or neither. Okay, so let's talk about the second derivative test. Okay, so if I have a graph that looks like this, okay, here are the points where f prime of x equals 0 and down here. Okay, so both of these points. Okay, I want to use concavity to tell whether I have a maximum value or a minimum value. I know it's a high point or a low point. It's a turnaround point, but I don't know if it's at a mountaintop or at a valley just by using the first derivative. Okay, so one way I can do it is I can say concave down, then I have a max. Okay, so for example, I would take the first derivative, set it to 0, get this value of x, and then plug that into the second derivative and see what the sign is. If it's concave down, I have a maximum. Okay, if it's concave up, I have a minimum. Okay, everybody understand what I'm going to do here? Okay, they've actually told me where the values are, where the first derivative 0. Okay, so these are my potential maxes and mins. But again, without looking at the graph, I don't know whether it's a max or a min. Okay, so I'm going to use the second derivative to tell me that. Okay, so here's how I'm going to do it. Okay, the first thing I need to do is I need to differentiate once. And these are polynomials, so I'm going to use the power rule. Okay, I'm going to bring down the 3 and multiply the 2 to get 6, drop the exponent by 1. So that's the derivative of the 2x cubed. Okay, and then I'm going to bring down the 2, multiply the 15 by 2, and drop the exponent by 1. The 6 doesn't give me anything. Okay, now the first derivative, okay, if I set this to 0 and I solved for x, I get these two values. I get 0 and 5. Okay, so they came from doing this. Okay, so that's how they got those. They took the first derivative, they set it to 0. So I didn't need to do this, okay, but I'm showing you how they got these numbers. Otherwise, it looks like they pulled them out of the sky. Okay, so they set the first derivative equal to 0, and they solved for x, and they got those values. Okay, now I don't know which is which. Okay, one of them's probably a maximum, one's probably a minimum. And locals mean in the general neighborhood. You know that polynomials typically have lots of hills and valleys like this, right? They keep going. Okay, so locals mean like in the general area of. Okay, this would be another local max. Okay, A global maximum would mean the biggest y value for the whole function. Okay, and we'll talk about those in a minute. Right now, we're just interested in where does the function turn around? Okay, and it's where the first derivative gives you a 0. Okay, so now I want to find out whether these are maxes or mins. Okay, and again, if the function's concave down at these values, I've got a max. If it's concave up, I have a min. So let's do the second derivative. Okay, so f double prime of x. I'm just differentiating the first derivative. So I'm starting with this one. Okay, so 2 times 6 is 12. Drop the exponent by 1. Okay, here my exponent is 1. Multiply the negative 30 by 1 to get negative 30. Drop the exponent to 0, and that turns into a 1. All right, so here's the second derivative. Okay, does anybody have questions on how I got the second derivative? Anybody questions on how I got the second derivative? Just differentiated the first derivative. Okay. Now what I need to do is test each x value. Okay, that made the first derivative 0. Okay, I'm going to test each x value. Okay, the first one, let's do x equals 0. Okay, so I'm plugging in a 0 into the second derivative. Okay, so that's 12 times 0 is 0. Minus 30, so minus 30. Okay, my second derivative is negative. What does that tell me about concavity? Anybody remember? What does the negative second derivative mean about concavity? Okay, it's actually, it's negative. Okay, the second derivative is negative because I plugged in a 0. Okay, to the second derivative, and that gave me 12 times 0 minus 30. That's 0 minus 30 is negative 30. So my second derivative has a negative value. Okay, and that tells you something about concavity, either concave up or concave down. Here's my little mnemonic frowny face, negative second derivative. See the two negative signs? Okay, that's concave down. Okay, and if I look at my little graph over here, what does concave down mean? Okay, does concave down mean I have a maximum or a minimum value?
Max.
Yeah, it's a max. Okay, so that tells you x equals 0 gives max local. I'll say local like they did. Okay, I didn't evaluate the function at 0. Okay, I can tell from looking at it, if I plug in a 0 here, I'm going to just get 6. Okay, but the idea is the local max is the y value. So you can write it as an ordered pair. This is an ordered pair. Okay, so local maxes and local mins are ordered pairs. But you must give the y value. You can't say it has a local maximum at x equals 0. No. Okay, either the X and Y or at least the Y. Okay. Well, hopefully then I should try the other value that made the first derivative 0 and plug that into my second derivative. Okay, so that's 12 times 5 minus 30. That's 60 minus 30. So f double prime of 5 is 30. Okay, that's a positive value of my second derivative, which means it's concave up. All right, so that means x equals 5 gives a local minimum at 5, f of 5. Okay, does everybody see how I'm using the second derivative to tell me whether or not these turnaround points are high spots or low spots? I'm using concavity. Okay, concave down, I'm on a mountaintop. Concave up, I'm in a valley. Okay, so see how to use the second derivative test. See how to use the second derivative test? Now you do. Okay, anybody questions? Because I'm going to ask you to do the next one. Okay, so they gave you the places where the first derivative was 0. I showed you here how to find those. Take the first derivative, set it to 0, solve for x. Okay, that's how they got these values. Okay, here's one for you to try. Okay, so I'm going to leave this for you right here. You don't need to solve the first derivative, get it to be 0. Okay, they did it for you already. Okay, so this is where g prime of x equals 0 here. Okay, so I need you to do the second derivative test. Okay, you try number 7. Use number 6 as a guide. And type done when you finish. Okay, you're using the second derivative to tell you where you've got maxima and minima, where the high spots and low spots are. take another minute or so. Okay, folks, I know not everybody's finished, and that's fine. Okay, glad to see that a bunch of you are done. That's great. But let's come together to make sure that we're all on the same page with it. Okay, so they've pretty much given me two values of x where the first derivative was 0. So now I need to do the second derivative test. So I need both derivatives. Okay, so let me do g prime of x. Okay, I'm going to use it's a polynomial. I'm going to use the power rule over and over again. Bring down the 3, drop the exponent by 1. For the second term, bring down the 2, multiply the -3 to get -6, drop the exponent by 1. And with a -9x, the exponent on that x is 1. Multiply that times -9. And when the exponent drops to 0, the x disappears. Okay, and again, as I mentioned to you before, you'll speed up taking derivatives of polynomials tremendously if you realize that each term drops in degree, right? The cubic became squared, the squared became linear, the linear became a constant. And of course, the derivative of the constant is 0, so that goes away. Then I differentiate a second time. So 2 times 3 is 6, drop the exponent by 1. And 1 times -6 is -6. The x exponent goes to 0, so it disappears. Okay, now what I need to do is I need to test each x value, right, that made the derivative, the first derivative, 0. All right, so I'm going to test each x value, and those values are -1, okay, and 3. Okay, and I'm going to test them by plugging them into the second derivative. So that's 6 times -1 minus 6. 6 times -1 is -6, minus another 6 is -12. Okay, so that's a negative value. Negative second derivative, concave down. Okay, so I know that g of -1 is maximum. Okay, and again, g double prime of 3 is 6 times 3 minus 6. That's 18 minus 6, or a positive 12. Okay, that gives me a positive second derivative. That's concave up. So I know that G of 3 is a min. Okay, anybody questions on 7? Did that agree with what you got? And if you're thinking, can I just look at this on a graph? Yes, of course you can. It should tell you the same information as this. But remember, every graphs are not going to be polynomials. Okay, and some graphs are a little harder to figure out. Yes, you can always use the max min functions and whatnot. Absolutely. Okay, but it's a calculus class, so I'd like to see you be able to do some of the calculus as well. Okay. Matches what you got. Great. Okay. Anybody questions?
I have a question.
Yeah, go ahead.
How could you tell which one's a local and which one's like a maximum or a minimum?
Okay, that's a great question. And again, it depends on the function. Like if you look at a polynomial function like this one, okay, we can graph this on Desmos. I'm going to go to Desmos briefly and we can see what that looks like. Desmos. Okay, so here's our polynomial. It's y equals x cubed minus 3x squared minus 9x. Make sure I have the right terms, plus 7. Okay, so I think that's the right. Yeah. Okay, so here's the -1, right? And we said that was a max. We were right, a local max. And we said that is a local min at 3. Now let me ask you, does the entire graph have a global, have a largest y value? Does it have a largest y value? Okay, take a look at this. Is there a largest y value?
Going to infinity.
Yeah, it shoots off to infinity. So no. So there's no global maximum. Okay, there's no global maximum unless you restrict the interval you're looking at. Okay, unless you restrict the interval you're looking at. If I look at the entire graph over the whole number line, you can see it shoots off, the y values shoot off to infinity. So there's no global maximum. But if I say I'm interested in the global maximum, say from, what's this over here? From -2 to +2. That's from here to here. Well, then the global maximum would be this one. Okay, does that make sense? If I just restrict it to a very small interval, okay, then the global maximum would
That
be
makes
this
sense.
local one. But if I'm talking about the whole graph, this one doesn't have any global maximums. Okay, same thing with global minimum, right, with min. Okay, I can't type, so I'm just going to talk. If you try to say, what's the lowest y value you reach, you see the thing shoots off to negative infinity as well. Okay, so there's no global minimum unless you're going to do the same thing. You're going to say restrict the graph to be between -10 and +10. And then it's a matter of whether or not, -10 is going to definitely, by the time I get to -10, I'm much lower than I would be here. Okay. So same idea for the minimum. Okay, same idea for global minimum. This type of graph doesn't have them. Okay, but let me just mess with the graph a little. Okay. Okay. Now let's take a look at the graph. I messed with the degree of the graph. And now you've got a 4th degree graph. Okay, so how about this one? Does this graph, entire graph, have a highest Y value? Does this graph have a highest Y value? What do you think? It's a 4th degree. Is there a biggest Y over all real numbers? No, right? Because look at the 2 arms on it. They shoot up forever. The Y values get big without bound. Okay, here is a local maximum, okay, at 0.34. Okay, but now let's ask you about the lowest value. Okay, does this graph have a smallest Y value? Yeah, it does. It's this guy right down here. Okay, this graph never drops below negative 64.527. Okay, so this point here, okay, 3.417, negative 64.527 is both a global and a local maximum. Okay, so I'm putting it in the chat. Is a local and global minimum, rather. Sorry. Okay, this point right here, it's one of the local minimums. Here's another one. Okay, but this is the lowest Y value the graph ever attains. So it's also a global minimum. Okay, does that help? Anybody have questions about global minimums, global maximums as opposed to local ones? We'll talk more about it in a bit, but I just want to make sure I answered Richard's question. Can I get some feedback? Yes, no, maybe?
No, I'm totally understanding.
It's totally good now? Okay.
Yeah.
Anybody else questions? So the answer is it depends on the graph. And it also depends on whether you're restricting the interval you're considering. Imagine it's a word problem, okay? And the graph is representing, I don't know, product profit. This could be our product profit graph, and we took a nosedive in the second quarter of 2020, okay? And I want to only be interested in, say, a couple of quarters. So I would restrict the interval, okay, that I'm looking at the graph in. Okay, and I'd want to find just the global minimum on that interval. Okay. Yeah, again, it depends on the model and it depends on the graph, right? Depends on the model and what interval you're looking at. Okay, depends on the model and the interval you're looking at. Okay, let's take a look at some other problems that I have here in the notes. Again, I'm not going to walk through all of them because we're running out of time. I'm going to skip 8 because 8's also a polynomial. I want to take a look at 9 just to get you in the swing of how you would do this, okay? This is where f prime of x equals 0. Now, if you were to differentiate this function, f of x equals x times ln of x, Okay, how would you start to find f prime of x? How would you start? What are you looking at here? Anybody? Okay,
We would have to get that ln of x to was it 1 over x?
basically you want to start by figuring out what tools are you going to use, right? You know a bunch of
Oh,
different
okay.
ways, to differentiate, and you've got tools for differentiating ln, and you're right about the 1 over x. But what about what you're looking at? What about x times ln of x? What is that? See the dot? I didn't have to put the dot there. But what is this? Is this all one function? So what's the dot in between?
Multiplication.
Yeah, it's a product. Yeah, it's a product of two functions. And you have something called a product rule. Okay, so you can't differentiate this in a lump. This is a product of a linear function, right? Like y equals x, and a log function. Okay, so you need to use the product rule. Okay, to remind you, okay, how that works. F of x equals, you could use g times h. I use u and v, u times v. Okay, so then that means my function u is my x function, and my v function is ln of x. Okay, if you remember how product rule works, okay, f prime of x is going to be the derivative of one times the other plus the first function times the derivative of the second, right? You just take each function and you multiply it by the derivative of the other function. So that's my product rule. That means I need u prime. Okay, this is x to the first, bring down the 1, drop the exponent to 0, x to the 0 is 1, so I have 1 times 1 is 1. Okay, and here's what you suggested, Gil, is the derivative of ln of x is 1 over x. So I'm definitely going to use that piece of information. Okay, so then I have f prime of x equals u prime, which is 1 times v, plus u, which is x, times v prime, which is 1 over x. Okay, so that's everything going into the product rule. Okay, I can do some simplifying with algebra. Okay, that's ln of x plus, and again, these two cancel out. Okay, that's x over 1 times 1 over x, that's 1. Okay, and again, I want to simplify it because I need to find the second derivative. Okay. Okay, so f double prime of x, don't worry, it's easier. It's easier because I simplified it. Okay. I'm differentiating this. The derivative of ln of x is 1 over x, and the derivative of 1 is 0. Okay, so the second derivative is just 1 over x. And now I need to substitute the value they gave me into this second derivative. Okay, and check the sign. So here's f double prime of 1 over e equals 1 over 1 over e. Okay, everybody all right with the substitution? What do I do next? Okay, I did the substitute part. Here's the 1 over e going in for x. Now what? Well, it turns out e is a number. You could evaluate this on a calculator, but you might remember that 1 over e is the same as this. Multiply by the reciprocal. So that's just e. E is a number that's about 2.7. Okay, so this is positive. Okay, you need to know what to do at this step. Okay, you need to first of all realize e is a number, it's not a variable. You could type this in to a calculator and get a number. It'd come out as 2.7 something, and you'd know, all right, well, that's positive. Positive means concave up. So that means f of 1 over e is a minimum. Okay. Everybody understand 9? Okay, not everything's a polynomial function. Okay, so again, please ask if you've got questions. Anybody questions on 9? Okay, I'm going to skip 10 and see what else is interesting here. Okay, let's take a look over here. All right, here's this derivative business again. Okay, number 13. Okay, we're looking at various x values on the graph. Okay, so here are our x values. Okay, and all this is asking you is decide whether these are positive, whether they're negative, or whether they're 0. Okay, so at 0, f of x is asking for the y value. Okay, f of x is definitely positive here. It's above my x-axis. The derivative is the slope of a tangent line. That looks like it's a positive slope. Okay, and then I need to look at the concavity of the function there. Okay, the function appears to be concave down there. Okay, so my second derivative would be negative there. Okay, so again, concave down. Okay, let's take a look at 1. Okay, what do you think about f of x? Okay, f of 1, positive or negative? What do you think? Anybody?
Positive?
Yeah, it's positive. Okay, so I'm going to put a plus there. Okay, how about the slope of a tangent line there? What's the sign on the first derivative? Okay, I think Richard's answering. It's a negative slope, so this has a negative sign. Okay, and then what do you think about concavity? Okay,
Concave
right
up.
at this point here. Can you tell if it's concave down or concave up? Okay, it's hard for me to tell. It looks like it might be concave up. This might be the inflection point, or this might be the inflection point. Okay, so not sure. Okay, some people are saying plus, maybe 0. Okay, if it's an inflection point. But it looks like the graph has a little kink right here. Okay, so I'm saying concave down may end there and concave up starts here. It's really hard to tell without doing calculus. Okay. All right, everybody kind of get the drift of how this works? Okay, let's just do one more of these. How about f of 2? F of 2. Okay, positive or negative? Okay, so f of 2, or I guess you're answering, Adam, positive? Absolutely. What do you think about the derivative right here? Yeah, 0. Okay, and now we need to look at concavity. Okay, so how about f double prime? Concave up or concave down?
Concave up.
It's concave up,
Yeah,
right?
up.
So remember our smiley face friend? Concave up. Okay, so what sign does the second derivative have? Look at the eyeballs. They're positive, right?
Positive.
Okay. That's how you do it. All right. Let's just take a quick look. We're getting near the end. Everything else in here is merely derivative practice. Okay. So we're just going to look at these so you can see how you would get started. We're not going to actually go through taking the derivative in class because we're out of time. Okay. But first, let me point this out to you. Okay. Take a look at y for number 14. Number 14. Okay. What derivative tool will you use? What derivative tool will you use? Yes, good for you, Miriam. This is a chain rule. Okay, this is a linear inside of a 5th degree. Okay, so you remember how that works. You take the derivative of the outside, leaving the inside alone. You multiply by the derivative of the inside. Okay, how about number 15? What will you do with number 15 first? What are you going to do with number 15? What exponent goes on those parentheses? Anybody remember? What's square root as an exponent?
3.
For square root, remember roots
square
give you fractions.
What is that? 2.
1/2. Okay, the root that you want to take is in the denominator of the fraction. Okay, and any power you're raising to is in the numerator. I'm not raising to a power, so I got a 1 up there. Okay, if I was taking a cube root, the power would be 1/3. Okay, now this one looks just like number 14, so I'm going to use the chain rule. Okay. Last one we'll take a look at is this one. Okay, what do you think? What have I got here in 16? It's number 16. Anybody have thoughts? Okay, what are the two things you're multiplying? If you think it's, I've got two conflicting ideas in the chat. One says product, one says composition. If you think it's a product, you have to come up with the two things you're multiplying. Okay, and they need to be functions. Okay, if you think this is a product of a log and a quadratic, then I'd ask you, what's the argument to log or to ln? Okay, you have to feed ln something. Okay, and if you say it's a product, you're missing the argument. Okay, this is a composition. Okay, this is a quadratic inside a log. Okay, so the argument to log is the quadratic function. Okay, so this is a composition, so you would need to use the chain rule. Okay, please practice looking at them and deciding what they are first. Okay, in order to be able to determine how to approach them. Right? Okay, questions on these last few? So that was 14 through 16. Questions on 14 through 16. I'll upload all of the work of doing them, okay? But again, the important part is to see if you can recognize what you're looking at. Anybody got questions on these? Okay, I'm not seeing any.
No, I'm good.
All right, I'm going to come back to the meeting and ask if you've got questions in general. Questions in general. Again, I'd encourage you, try the homework and email me from inside the homework if you get stuck.